Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss about the velocity distribution for turbulent flow in smooth pipes. In our previous video lecture, already we have discussed in details about the velocity distributions for turbulent flow, and which is, that equation is applicable for smooth pipe as well as the rough pipes. And already we have discussed that one, and we got that equation like U equal to U star by K, and this is log E y plus C, and this is the equation actually we have got previously from the derivations. The derivation of that is actually velocity distribution for turbulent flow. That equation we got, and that is going to be used in the smooth pipe. Then we'll discuss about the rough pipe also. Now we know that this equation actually where it is applicable. So this U is, we know that this is local velocity. This is local velocity, and U star, if you remember, or you can see that video, what is that value of U star? U star is nothing but this is shear velocity. This is actually shear velocity, and y is the, you can say that height. What is the height, how much we are taking from this surface of the pipe. So now, so let me draw a pipe here so that you can understand a little bit more. Suppose this is the pipe, and in this pipe, this is the suppose center line of that, and the water which is flowing, or the liquid which is flowing through this pipe, okay, as we know that near to the surface of the boundary we don't have that much velocity of flow will be there. So here near to this we used to consider the velocity is equal to 0. Okay, now at the height of this y we have taken, and the previously this height y was taken here, and previously I have shown that the similar things also, and we got three different zones, and three different zones how we used to given, like this also we have discussed, like laminar zone and turbulent transition zone and turbulent zone. These things also we have discussed, and there we got in the turbulent zone one laminar sublayer. Okay, laminar sublayer we have got in this, and in this sublayer actually the roughness, what we are talking about the smooth pipes and the rough pipes. So in this laminar zone, in the turbulent zone only, this sublayer formation will be there, and the sublayer actually, this laminar sublayer height is delta dash, and this in the laminar sublayer we used to find this smooth surface and rough surface. So which was detailed discussion has happened in the previous video lecture, so you can see once that one, so that next step derivation you can understand that. Now here, as I told you, this is the local velocity, and this is U star is the shear velocity, and this is the constant. What is that constant? That is the constant actually kappa constant is there, and this constant K value is we have taken 0.4, and this K actually, this is the distance is to there in the height of roughness, you can say the height of roughness which was to there. If you consider this is the surface, and the fluid which you used to got, it used to like that you can consider. Okay, and here the height of this irregularities, this is actually K, height of the irregularities. Anyway, so these are the values are there, and this is constant. This is the constant value. Now you can see at this y could see this distance we have taken here, okay, in the pipe. So here at this y, if you see, this is 0 point, and with the height of some value is there, some y equal to y1, y2, y3, some value will be there. But at this y equal to 0, if you see at y equal to 0, okay, at this wall, where this at this pipe wall, if you put the value of y here, then what will get here? The value will be minus infinite. Okay, if you put the value of y equal to 0, then what we are going to get? Now velocity at the wall, we are going to get minus infinite. So that means what? Now at this wall, if you consider for this equation, the smooth pipe, then at this condition, we won't get the value of velocity near to the wall, because as per the equation, if you put this value of y, then we are getting u equal to minus infinite. Okay. Now, so what is the meaning of this? That means the value of u, that means the velocity v or u we can consider, no issue, will be positive. See, here we are getting minus infinite. So, now, so if you go a little bit away from this, if you go a little bit away from the boundary surface, then we may get some positive value, because here we are getting the negative value. Okay, so this minus value will be omitted or neglected if you consider the value of y, okay, with a distance of suppose y dash. Suppose with a distance of y dash, then you can take this one. Now for this, what we will do? Let's put the value of this y dash in this equation. So what we'll get here? Already we kept that value of 0. So that above equation, what will there? 0 equal to, you can keep u star by, in this k value also we can keep the value of 0.4, we can keep only k, and this is log e y dash plus c. Now what we'll do here, we'll find out the value of c. So c is nothing but, okay, c is nothing but what we can write, just take this value that side, so that will be minus u star by k log e y dash. So this is the equation. Now what we'll do, just put this value in this equation, this c value, put this in this equation. So what we'll get here? U equal to u star divided by k, and this is log e y minus of this, minus of what? Now u star by k log e y dash. Now you see here u dash, u star k is common term is here, and then it will be there log e y minus log e y dash. So this one we can write what? U star divided by k, and here you can write in the bracket, or you can write in such a way log e, this in log e y minus log e y dash. So this one you can write log e log a minus log b, that we can write log a by b. So that is nothing but log y by y dash. Now let's put this, as I told you, the value of k, kappa constant value is there, k equal to 0.4. Let's put this value of k in this equation, So what will get? U equal to u star, this one. Now if I put the value of 0.4 here, then that means 1 by 0.4, which is nothing but 2.5. Okay, so directly I can write here 2.5 u star, 2.5 u star, and this is log e y by y dash. So this one you can write in this equation. Now what I'll do again, I'll just take this is only the velocity, the local velocity what is there, and now let's take this u star also, other side, u by u star. So what I'll get here, 2.5 log e y by y dash. Now what I'll do, I'll again change this, convert this log e terms in terms of log 10. So that log e terms will be changed into log 10, means we know that. Again, let me write. So log, suppose e, and this is y by y dash is there. You can give this is a square bracket. So what we'll get here, log e y by y dash. So we can write log, this one I can write 2.3 log 10 y by y dash. Same, this will be same, only these things will be changed, remaining things will be same. So we can write here what, in place of this I can write 2.5 into 2.3 log 10, and this is y by y dash. Now if you multiply this, we'll get the value, we'll get this value, you know, you can write u by u star equal to, this is 25, suppose 25 into 23, so 25 into 10, 25 is 625, and remaining 2 less is, that is 600, 575. So this is 575, and this is log 10, and this is y by y star. Now this is the equation what we got from this previous one, from the velocity distribution for turbulent flow. Now this equation again we can give a equation number. Suppose initially we have given equation 1, now we can give the equation 2. Now for the smooth boundary, if you see, so you see smooth boundary and rough boundary already we have discussed previous derivation time. So there actually this is the surface is there, suppose, okay. So which is called smooth, which is called rough, already we have discussed previously, okay. Now this is the value, this is the layer, okay, this is the layer, and this layer is nothing but delta dash. So here this is the delta dash, this is nothing but laminar sublayer. So sublayer value, and this is k value, correct. When the k value is less than the delta star, then it is called smooth surface, and when this k value is more than the delta star, that is called rough surface. We already discussed previous in the last videos. So here if you see, if the laminar sublayer exists for the smooth boundary, okay, there is a laminar sublayer is there. So the velocity distribution in the laminar sublayer, okay, we have seen that parabolic in nature in the sense, okay, let me tell you. And one more thing actually I have, let me inform you. So what value we got here, okay, y equal to y dash, that means the nature will be started not from the origin, okay, not from this point, okay. So that will be started from here. Which nature? Nah, the parabolic nature, because if you have seen that for pipe actually, let me draw it here, okay. Suppose this is the pipe is there, and this is pipe, let it close it, and this is the suppose center line is there. As we know that near to the boundary, near to this surface boundary, the velocity is 0. So the curve will be started like this, you know, the curve will be started like this, and again it will be maximum at the center line, center of the pipe. Similarly from this, if you consider, again it will be like this, it will be started from 0, again it will be maximum here, like that it will be close. But as you have seen in this equation, if you put the value of velocity equal to 0 at this y equal to 0, what is the velocity value? Now we are getting in minus infinite. So that we have taken y equal to some distance, so that we will get some positive value. That means that this curve will be started from this some distance of y equal to y dash. That means what I mean to say, that graph will be there like this, you know, it's supposed to be started here like this, okay, and this will be the velocity u, you can say this is the velocity u, and this is the distance y equal to y dash. Now it is not started from the origin actually, now it is not started from the origin, from here it started from this point. So that's why, yeah, see, this is the y equal to y dash, and I can write the total height of this, suppose y, suppose this is total height. Now for this point where it started on behalf of 0 here, it started from with a distance of y equal to y dash is started. Now at this, because we know that at here if you start from here, we'll get y equal to 0, and we got the value of u equal to, you know, minus infinite, we got this value, correct. That's why we have taken here. Now why I'm telling these things to you, because here the equation what we got here actually, so that will be applicable for this smooth pipe and as well as for the rough pipe also, okay. Now for the smooth pipe actually, we need to consider the velocity distribution for the laminar sublayer is parabolic in nature. We know this, parabolic in nature. The velocity distribution for the laminar sublayer is parabolic in nature. So that if you see in the laminar sublayer, the logarithmic velocity distribution, logarithmic velocity distribution, okay, does not, it is not able to consider or not depending on that. So we can say what it comes in that. So here this y, see, it is not directly linear, you can say, okay, like that it is curve is there. That means you can say that y is the function of, you can say, the log, is a function of log, we can say log y, okay. So this is the linear function of log y, you can say. So here if you see again, one more point is there. So you can assume that the y dash is proportional to delta. Y dash is proportional to delta. That means, see, y dash is where? Now y dash is this one, correct? Y dash, why we taken? Now y dash, because of this velocity at this point was 0, and at this point velocity is infinite at this point of height y. That's why we have taken a y dash. But if you come to the sublayer region, if you see, this is the laminar sublayer. At this sublayer region, this is delta dash. So inside this delta dash, we have the smooth surface. So smooth surface is the value of K should be less than this one. So what it meant to say, because when the flow is turbulent, so there of course we have a laminar sublayer will be there. So that's why here what I meant to say, the y dash is directly proportional to the delta star, we can say. So the delta star, we know that is the thickness of the laminar sublayer. And again, that scientist Nikudse experiment, he given some value of this y dash actually. Again, that Nikudse done some experiment on these, and he found some value of y dash from this from his experiment, and he gave some equations of y dash that we'll see. Yeah, now I can write from the Nikudse equation, we can write y dash equal to delta dash by 107. Actually, this is the equation which was given by the Nikudse, and how he got? Now from the by doing some experiment, he found this value actually. Because see, this is an experiment, means we need to do number of times. We won't get exactly at a single time, because the y dash, you can see, as it is directly proportional, because here see, y dash is for this one, and delta dash is nothing but the laminar sublayer, correct? So here what he got, y dash value he got delta dash by 107. Again, what is the delta dash value he got? So what is the delta dash value he got? Here the delta dash equal to 11.6 nu divided by u star. 11.6 nu by u star. So we know that u star is that shear velocity, and nu is nothing but kinematic viscosity. So kinematic viscosity, we know that mu by rho. Okay, so this is the value of delta dash. Now what we can write? I can write y dash equal to 11.6, and this is nu divided by, just put the value of in this equation. Yeah, 11.6 nu, and this is u star into 1 by 107. So if you get this one, so finally what we'll get here, 11.6 by 107. So near about it, no, 10 point something will come. So that means 0.107 something will come in, because 116 by 107 is there. So you'll get here actually 0.10, 0.108, one something will be there like this. So you can write nu divided by u star. Okay, this is the equation of y dash. Now what we'll do, the previous equation what we got here, this is the equation actually. In this, if you see, y by y dash is there. Okay, y value we know that it will start from this base point. Now y dash we don't know. Okay, so we can now what we'll do, we'll just put this value in this equation, in the previous equation. Okay, substitute this value of y dash in the equation of 2. Then what we can write here, again it will start u by u star equal to 5.75 log 10. Here we can write y by 0.1081 nu by u star, correct, and this is bracket, let it close. Now if you see this u star, you can take it to the numerator and we can write again 5.75, and this is log 10, and this is u star, and in the denominator what will be there, 0.108 nu, bracket close. Now again these things what I can write here, I'll do one thing. This is 1 by, suppose 1 by 0.108 is there. Again we can write that one. So one more line let me write 5.75, this is log 10, and this value let write u star y by nu, and this one we can write 1 by 0.108, so that is nothing but I can write 0.9, okay, something like 0.925 will be there, that is okay. We'll do one thing, we'll calculate this, that is better. Yeah, so this is 1 divided by 0.108, 9.25. Okay, so you can write this is 9.25. This is the value we got here. Now again what we'll do, you can write this value in terms of, again just will write in terms of what, 5.75 log 10 u star y by nu, again because see this is log ab we can say, so log a plus log b, so you can write in this way also. So again 5.75 log 10, and this is the value 9.25. Now finally what we'll get, so finally the equation will be there, u by u star equal to, you can write 5.75, this is log 10 u star y by nu, and this is 5.75 log of this one, we'll get the value 5.75 into multiply of this one, we will get 5.5. Okay, you can also solve it in here. So here also the mode is there, function is there, you can calculate from that also. Okay, so if you want to calculate, just put the value of this, how much this is, into 5.55. So you can write plus 5.55, and this one you can give equation 3. So this is the velocity distribution, you can say, for the rough pipe, for the smooth pipe is there. Now as I told you, so this equation can be used, okay, for rough and smooth both. Okay, now we'll see quickly, we'll see this velocity distribution for the turbulent flow in the rough pipes. Rough pipes already I told you here this is actually smooth pipe, but when this value will be reduced, for the rough pipe, let me draw it again here. Suppose this is the surface is there, and in the surface we have this roughnesses are there like this. The fluid roughnesses are there like this. So here, if you see, our laminar sublayer will here, but our irregularities in surface, the height of the irregularity is k, and here it is delta dash is this one. That means k is greater than delta dash. For this condition, we used to call this is a rough pipe. Okay, so for this rough pipe, if you see, you can say that is laminar sublayer is very small. Okay, so again for this also you have to use this equation actually, u by u star, or that is 5.75 log y by y dash. So let me write that equation actually, then I'll tell you what need to be done. U by u star equal to 5.75 log 10 5.75 log 10 y by y dash. This is y by y dash. This is also same thing. Correct. Same equation need to be taken for the rough pipe also. As I told you, the height of this is the height of k, and which is more than the laminar sublayer. So laminar sublayer is very small. Again, you could say done some experiment, and he found that the value of y dash actually y dash for pipe coated, because see when the pipe will be there, we used to get in the roughness in the pipe only. Okay, this, so the roughness will be identified at the surface of this is very very small will be there. So that y dash for the pipe coated with the uniform sand, this pipe will be coated with the uniform for that condition actually. For that condition, the y dash what you got the value of k by 30. Okay, this is the value. Now what we'll do, just put this value in this equation, that's it. So 5.75, this is log 10, and this is y by k by 30. Now just to take this value in the top, or you can write what is in, let me directly write 5.75, and this is log 10. Okay, and this one we can take log, that means y by k, because see this one more step can be written, just I'm skipping this one. That means the 30 I have taken here to the top numerator. Then what we'll get again, same thing, 5.75, and this is log 10 into 30, because what will be here, just I'm writing here 5.75 log 10, and here I can write y by k into 30, like that I can write. Then what will happen, now log a into b, so log a into b we can write log a plus log b, log a plus log b. Okay, 5.75. Now we'll get the value for this one. So finally we can write u by u star equal to 5.75, this is log 10 y by k, and this value we can write, this value will be there log, okay, sorry, so value need to be required log of this multiply of 5.75, so this is 8.49. That means we can write this 8.5, no issue. This is the equation for the velocity distribution for the rough pipe. So equation 3 completed. Now we can give it equation 4 here. Okay, so I hope you understand in this. So it's very simple actually, but before going to derive this or to understand this, some previously I have discussed about the velocity distribution for the turbulent flow only, and some derivations also done, and just you see that video so that you can understand how, from where this equation actually taken. Once you understand this equation, then we can go for the conditions here. What are the conditions what we have taken at y equal to y0, y equal to 0, then what the value of U. So then we can go for the next step and we can find out the velocity distribution for the turbulent flow in the smooth pipe as well as for the rough pipe. So I hope you understand this concept. If you're having any doubt regarding this, you can give a comment on the comment box. Thank you all.